The topic is type of semiconductors based on its purity. Now, based on the purity, there are two types of semiconductors. One is called intrinsic semiconductor and second one is called extrinsic semiconductor. What do you mean by intrinsic semiconductor? Semiconductor crystal in its pure form is called as intrinsic semiconductor. See, you take silicon, and silicon is available in the form of ore in nature. What you do is you take the ore and it will be not in purified form. So a silicon crystal or ore will consist of many other atoms also. So what you do is you purify it, and it is actually not an easy task. You purify the ore, and how much ever you purify the ore, there will be small amount of other atoms also. But let us say if you are able to purify the ore, it consists of only the silicon atoms, then that type of semiconductor is called as intrinsic semiconductor. So that is why it is the semiconductor crystal in its pure form. So this is the example is purified silicon and germanium. Now the second one is called as extrinsic semiconductor. Here the semiconductor crystal with some amount of impurity. This is not naturally added impurity. This is purposefully we are adding the impurity to become one more type of semiconductor, that is called as N type, and actually another one that is called as P type semiconductors. By adding a few number of impurities, we are getting another type of semiconductor actually. Now we are going to discuss about the intrinsic semiconductors now. See, this is the crystal structure of an intrinsic semiconductor. So I have taken example of a silicon atom, system of atoms. Now the silicon atom will have 4 valence electrons. Each valence electron will be bonded with the valence electrons of neighboring 4 semiconductor atom by means of a bond. That bond is a covalent bond. So this is a covalent bond. Actually, how it happens? See, when you take a system of atoms, so here there is one atom which consists of 4 valence electrons, 1, 2, 3, 4. Here also this consists of 4 valence electrons, 1, 2, 3, 4. And here also it consists of 4 valence electrons, and here. So let us say there are 5 atoms. Now you take this one electron, it will not revolve around this semiconductor atom. Since there is a bonding, this valence electron comes like this, like this, like this, and like this. So this will go like this. Similarly, one electron from this atom also will go like this around this atom. Similarly, one from here will go like this. Another from here also will go like this. Similarly, here also, the electron which is here will go like this, one electron. Similarly, one electron will come from. So, actually there is a bond between the valence electron of this and this. Here there is a bond, and there is a bond between the valence electron of this and this. There is a bond between the valence electron of this and this, and there is a bond between the valence electrons of these two. So that is what is represented here. See, this is the valence electron of this silicon atom that will be bonded with the valence electron of its neighboring silicon atom. Similarly, here also, here this is the silicon atom, this is the valence electron of its neighboring. This is the silicon atom, valence electron of its neighboring. So this will continue actually. So this is the structure at absolute zero. This is the structure. Now you don't find any free electron. All the electrons are revolving around the nucleus itself. So the electrons are within the atom. So all the electrons are in the valence band itself with different energies. Like this. Okay, now this is the forbidden energy gap, and you don't find any electrons in the conduction band because the electrons are not free. So this is the structure at absolute zero. So this is an energy level diagram. So we can say that the conduction band is empty. So therefore at absolute zero, what happens is all the semiconductors behave as insulators. All the semiconductors at absolute zero behave as insulators. So the conduction band is completely empty. So therefore there is no conduction. But this is at absolute zero. But at room temperature, what will happen? Room temperature is very much high compared to absolute zero. So few electrons which are at higher energy, see here. Okay, all the electrons revolve around the nucleus like this, or like this, or like this, or like this, whatever. The electrons which are at higher energy, so what will happen when they go like this, they get energy and they will come out. Once they will come out, they are not controlled by the nucleus, so they are free. So what will happen is now the energy level or the energy of those electrons will be more compared to the energy of the remaining valence electrons, naturally. So when the valence electrons acquire energy, those electrons will go from the valence band to the conduction band. This electron goes here and the energy of this is high, and we say that the electron is in the conduction band. Now what will happen in the valence band? There is one vacancy of electron because this atom lost one electron. Now what will happen is here the vacancy of electron will be created, and this vacancy of electron is called hole, and this electron is called free electron, and these electrons are called valence electrons. So valence electrons are different, free electrons are different. Now when the electrons acquire more and more energy, more and more electrons will go from the valence band to the conduction band, and here the corresponding holes are created. Now if you see the number of electrons and holes, they are equal in number. So we say that number of electrons will be equal to number of holes, and at room temperature that is a constant, that is called intrinsic carrier concentration. So Ni is called intrinsic carrier concentration. That will give you the number of free electrons or holes at room temperature. So here what will happen? Coming to this here, same thing I'll explain here. Let us say this electron acquire energy and this will come out of the bond here and creating a hole. So the electron hole pairs are generated. So this is called as electron hole pair because they always exist in pairs. One free electron give rise to one hole. Now as the temperature is raised, what happens? More and more electrons acquire energy and more electrons go from the valence band to the conduction band. And when the number of electrons in the conduction band increase, the conductivity also will be increased. So as the temperature is raised, conductivity increases and the resistivity and or the resistance of the semiconductor decreases. That is why these semiconductors have got negative temperature coefficient of resistance, unlike in the conductors. What will happen in the conductors? As the temperature is raised, the resistance will increase, but here as the temperature is raised, resistance will decrease, and the resistance will decrease exponentially, and the number of electron hole pair will be equal to T to the power 3 by 2 into e to the power minus Eg divided by 2 into K into T. So where T is the temperature in Kelvin, degree Kelvin, Eg is the forbidden energy gap, K is the Boltzmann's constant. So you can see here the number as the temperature is raised, the number of electron hole pair exponentially increase. You can see that. So therefore it is not linear increase. So the number of electron hole pair will exponentially increase. And therefore what will happen to the conductivity? Conductivity also exponentially increase as the number of, as the temperature rises. Now this is the crystal structure. At room temperature, what will happen? There will be many number of electron hole pairs. Now when you apply the electric field to this semiconductor, what will happen? These electrons are free and those electrons are drifted toward the positive of the battery. So what will happen when they are drifted toward the positive of the battery? There will be conductivity, and the conductivity is due to the electrons. So we say that the conductivity I will be equal to, or the current will be equal to the current due to electrons. Not only this, see here, there are holes. Now when the electric field is applied, what will happen is the electrons from one bond may come and occupy this vacancy. Now what will happen here? The vacancy which was here has been shifted to this. Now here also what will happen? There will be movement of electrons. Okay. So what is the current now? Now because the electrons move from one place to the other place and occupy the hole, there will be the current. And that current is due to the movement of holes, and therefore that current is called hole current. So therefore the total current will be the electron current plus hole current. Actually holes will not move, effectively the electrons will move, but we say that the holes are moving. Okay, that is why in a semiconductor the current is due to both the electrons as well as holes. But in the case of a conductor, the current is due to only one type of charge carrier, that is electrons. But in the case of a semiconductor, the current is due to both electrons and holes.